Thank you for having me, and I should actually thank Olivier Boissier for giving me the opportunity to present work we did in the ENFIELD project. Um, One of the research pillars of ENFIELD is green AI, and what I'm going to talk about is um, systematic literature review we did about the intersection between AI and life cycle assessment. I'll introduce this concept briefly. When we think about AI and the environment, the first thing that comes out is that we have much more evidence of the benefits of AI compared to the drawbacks of AI and the negative environmental impact of AI. It's quite clear in this picture, where what you see are the Sustainable Development Goals defined by the United Nations. And on all aspects, including the environment, on the left, you have the positive impact, on the right, the negative impact. And what is visualized is the level of evidence of impact on each development goal. But it can mean two things. Either that AI is indeed undisputed in its benefits, or that researchers actually only look at the positive impact of AI. And there are suspicions that we're actually biased as researchers towards the positive impact of AI, and I'll give two reasons. Uh, the first reason is in the next slide. Um, you might have seen this picture or a similar picture that shows that the cost to train a machine learning model has grown exponentially over the last decades, especially with the language modeling in the past few years. And that cost comes with an increase in uh, energy consumption and eventually of carbon emissions. Now to the second reason why we might be biased. The main cloud operators and the main service providers, and here I'm talking about Google, Amazon, Meta, Microsoft, see their operational costs, so their energy consumption basically, increase dramatically. You can see the orange curves in this figure correspond to the operational costs these companies report, and it increases despite the target they define themselves to reach net zero emissions in now a few years, in 2030 for some companies and 2050 for the others. And that's the purple curves, purple lines you see. Targets are um, defined such that emissions are supposed to decrease, but companies spend more money, spend more energy, and emit more CO2 year after year. So we might have overlooked the negative impact of AI with respect to the environment. And that led to this systematic literature review. I can go to the next slide. Thank you. Now, how should we account for all the impacts, environmental impacts of AI technologies? There is a well-known methodology for that, and that's life cycle analysis or life cycle assessment. And it is comprehensive in the sense that it identifies every possible impact of every activity that led to an AI service and every product that is necessary for this AI service to be provided. And that includes mostly, in the case of AI services, computing devices over all phases of building and using the AI service. That includes learning a model, computing inference, but also managing data and acquiring data. All of these phases required computing devices, And each device has an environmental cost during its production, its use, but also when it's decommissioned and sometimes recycled. Yes, next slide, thanks. So LCA, life cycle analysis, is a way to account for all possible impacts of AI, but only on the direct impacts. But there are also indirect impacts that are induced by behavioral changes in the way we use an AI services, and that these changes also have an impact. For instance, we might be encouraged to use our car more often if cars become more efficient, and that leads to an increase in carbon emissions. This is a rebound effect. It's been well studied for several decades. And with this systematic literature review, we wanted to evaluate whether we could estimate, predict higher order impacts, indirect impacts of AI technologies by extending LCA. And the first step is, of course, to know what researchers say about AI and LCA. Next slide. We started with a very simple bibliographic search. We took all papers that include two terms, AI or machine learning. We also included that term, and LCA. LCA as in life cycle analysis or life cycle assessment. And we got roughly 250 papers. The first thing we did was to classify these papers into four categories. The first category is papers that talk about AI as the central LCA process. So that's the larger box. What we're evaluating is the entire AI service. But there are also papers that talk about processes or products and services that use AI, but are not focusing on AI. That's the second category. AI is in some upstream process. That's the box on the right of the figure. Here the focus is the application, service, product, and not AI itself. We have another case, the third category. AI is in some downstream process. That means that we're talking about digital equipment. We're talking about infrastructure that would allow an AI service to be provided, but the focus is not AI itself. And there is a fourth category which is not represented here because because AI is outside the scope of the LCA. AI helps performing a life cycle analysis, but it's not included in the analysis itself. So we're not evaluating the environmental impacts of AI in this fourth category. And the result we get is quite clear. I forgot something. You can move on to the next slide. I'll give an example for each of the categories, an example of paper we found. First category is AI is the main LCA process. That means we're talking about AI and we want to evaluate its environmental impact with LCA. The example is on the left, a paper entitled Is TinyML Sustainable? We're talking about TinyML, tiny machine learning. That's a technique within the field of AI. And we are calculating the carbon impact of various configurations in TinyML. The second paper to the right talks about biomass pyrolysis. The journal it's published in is Digital Chemical Engineering, so it's not written by computer scientists, and it still talks about AI. It talks about AI as a way to predict the behavior of pyrolysis as a transformation technique, as a chemical process. And there is an LCA performed for pyrolysis with different configurations with and without AI. The third paper that's in the next slide um, takes AI as a downstream process. Here it's, as you can see in the title, spatial temporal embodied carbon models for the accounting of computer systems. The focus is computer systems, not specifically AI, but actually evaluating correctly the environmental impact of computer systems in general is essential to properly assess the impact of any AI system. And finally, the fourth paper is a review on machine learning algorithms for life cycle assessment. Um, and in fact, there are a lot of proposals, a lot of papers that introduce machine learning techniques for LTA. And that's clear in our review. And that's the next slide. Most papers we found by simply looking at papers including AI and LCA as keywords, focus on using AI to produce LCAs. Essentially, when we want to perform a lifecycle analysis, we need a lot of data, and some of this data is not available. So we use machine learning to fill in the gaps. And that's a good illustration of the bias we have as researchers. We don't include AI itself in the LCA, and yet it might itself have an impact. And that's why we, in a second step, looked at all the papers that are not in this category. So here the numbers are higher, but in the end we selected 43 papers that consider LCA for AI and not AI for LCA. And you can move on to the next slide. Thank you. A first observation we made on these 43 papers is that there aren't many application domains for this particular configuration where LCAs are made for AI systems. There's construction, and especially the manufacturing and recycling of concrete. There is waste management. I already gave the example of pyrolysis. This is something that is regularly mentioned in papers, and the other is methanation. There are a few papers about something that is seen as a very important technology by the European Commission, which is carbon capture, utilization, and storage, CUS. And then we have some miscellaneous application domain. There is, of course, regular mentions of digital infrastructure, but we have also solar power generation, additive manufacturing, agriculture as application domain. I'll maybe skip these two slides. This is an illustration from two papers about how AI can be used in LCA, but I'll skip that. To come to these numbers, another insight we got from our review is that most papers assess the environmental impact only in terms of carbon emissions. You might also have heard about the importance of water use when talking about the environmental impact of data centers. And it's actually only looked at in few papers. The diagram on the left shows that more than half of the papers only look at carbon emissions, and the others look at a few more criteria, including water use, including land use, the fact that we build something on land that could have been used for agriculture. Um, and the other criterion we find is what's called abiotic resource depletion, which essentially means we need metal to produce computing devices that are then used in AI services. Something else on about the diagram on the right in the previous slide. Yes. It's still preliminary results that I'm showing you. And this might change, but it already gives a hint at the results, the quantitative results of LCA for AI systems and AI services. You can see that there is no clear benefits of AI when we use LCA as a methodology. The positive impact is only assessed in less than a third of the papers, and in most papers, or the most represented category is the category of papers where the impact is actually not quantitatively assessed. LCA is mentioned as a way to do it, but there is no quantitative results. And this is another, this is evidence that we are biased as researchers, and more research should be done on the actual negative impact of AI with a clear methodology. Other things that I can tell you, and that's in the next slide. Another thing that I can tell you is that researchers, not computer scientists, but other researchers, mostly think of AI as AI of the last decade. The most represented techniques in the papers we found are decision trees, gradient boosting, simple neural networks, multi-layer perceptrons, genetic algorithms. This is essentially all the techniques we can simply get with scikit-learn. And there is only few mentions of advanced models, for instance, language models. It's mentioned in only 5 papers out of 43. And there is only one mention of a more complex model, which is variational autoencoders. That's the bar to the right of the figure. And this bias of other researchers toward simple AI is something that we already know. The picture on the right is taken from a recent report, but it actually was already reported by the climate change AI community something like 5 years ago. Most benefits of AI are achieved with simple AI, scikit-learn AI, and not with generative AI. That's a clear distinction. Next slide. I'd like to finish with an opening towards technological symbiosis. I said at the beginning that we wanted to go beyond LCA as a way to assess the environmental impact of AI, and to look at the indirect effects of AI through behavioral changes. And typically, technological symbiosis can help us go beyond LCA. Technological symbiosis is the interaction between two technologies that amplify each other, as in symbiosis in natural ecosystems. What it means is that there is an infrastructure that allows an AI service to be provided, and this service itself encourages to use more of the infrastructure. And we found several technological symbioses in our corpus, and I'll give two examples in the next slide. On the left, you have a paper partly written by Meta researchers who are the only ones to talk about the variational autoencoder I mentioned a few slides back. They used this kind of neural network to predict the property of concrete mixes so that they can build a data center. This is a typical example of technological symbiosis where AI is used to produce, to build data centers, which themselves are only justified by the fact we will use more digital technologies, will produce more data, and eventually will use more AI techniques. And this is not evaluated at all. The impact of constructing this data center in the paper. On the right, you have another example of technological symbiosis about e-waste management. Here, the AI system that is being used is much simpler. This is a classification model to better sort e-waste and encourage reuse when possible and recycling of parts of electronic waste. This is another example of symbiosis because the more we can reduce the impact of producing hardware with a simple classification model, the more we'll be inclined to use hardware. And this is a kind of interaction that typically leads to a rebound effect. We actually produce more hardware, which has a higher environmental impact. And again, the perspective of producing more hardware through this efficiency gain is not discussed in that paper published in the Environmental Impacts Assessment Review. And that'll be my conclusion. The trajectory that these technologies enable are usually not discussed. They were actually never discussed in the corpus we have. And this is a clear this is the opening I want to make. The reason why certain technologies are developed and the potential indirect effects they have should always be discussed after an LCA is being done for any AI system we want to talk about in our papers. Thank you. And I guess the questions would come after Enzo's presentation.
Okay, so we will join the question and answer session. I'm gonna try to share now my screen. Let's see. Okay. So yes, there we are. So my name is Enzo Tartaglione. I am full professor at Telecom Paris, Institut Polytechnique de Paris, and I work within the ELIAS project. And my talk will be a little bit more technical than the one offered by Victor, which was, I think it's important to take into account from the global picture, how is all of this use of AI is really impacting our world and what we should consider from a perspective of low carbon impact. I work with the deep neural networks. Therefore, I'm more on an engineering side. And I'm going to talk with you about, very quickly, about something that I've been doing since the end of my PhD, actually. It's reducing the complexity of a deep neural network. And there are multiple ways of doing that. My favorite one is pruning, which actually didn't come up with a deep neural network, actually is much older than that. It's even older than machine learning itself. So if you heard about that very recently, and by very recently, I'm gonna say 11 years ago, I mean, it means just that it got popularized for deep neural network by a work that we're gonna review together. What I will be doing in the next 20 minutes is to prospectively open a little bit your mind and invite you to reconsider how pruning could be really perceived. So, as maybe some of you is also familiar with this plot, this was very popular around 2020, 2021. It comes from a famous survey and actually shows the trend of deep neural networks in the last, in the previous 5 years on ImageNet 1K. So the version of 2012. And what is showing is not only that in terms of accuracy, we were gaining a lot, but also in terms of size of the model, we were growing. Of course, when we want to gain in generalization, since we were in a so-called underfitting regime, we needed to add more complexity to the model. And of course, around 2019, 2020, computer vision got revolutionized by the application of transformers to vision. We saw later that this is justified by the fact that we want to have multimodality, and use of transformers is very convenient for that. But consider that this is up until 2021, and the size of the dot is proportional to the complexity of the model somehow. So the biggest dot is the smallest dot that you see pre-2022. That's a transformer model. It's for text, because as we all know, in 2022, our life as a researcher also, but as a person living in the world, got impacted by the open sourcing of large language models. And so the largest dot that is close to the smallest dot here became much, much larger. Therefore, the models that we played with in 2024, 2025 are huge model complexity. And yeah, of course, we can talk about the complexity of training this model, complexity of using these models. From now, I'm just stopping saying, okay, these models are huge. And the bigger the model, very roughly speaking, we can say the more it consumes. And that's the kind of perspective that I want to offer you. So especially in 2025, a lot of effort has been done to reduce the model complexity. We can talk about energy consumption. We can talk about memory utilization. We can talk about the complexity of computation that we require to really run these models. So we have multiple ways. Probably the most popular one is knowledge distillation, because essentially last year, a big part of the community was doing essentially that, meaning take the big model and try to squeeze all the information in a smaller model that consumes less. That's one option, but what I will be talking with you about is pruning. What is pruning? With pruning, we mean simply taking a big model and we try to reduce the number of parameters of the same. And how do we choose the parameters? We can just chop them individually, or we can chop them in groups. And of course, how is it different with respect to the sparsification? Well, concretely, no, there is no difference between the two of them. Sparsification relates to the way the parameters in the model are represented. Normally it's a tensor, and so we obtain a sparse tensor in the end if we start doing pruning. So the two concepts are really related each other. But keep in mind that every time that we are removing a parameter from our neural network, since this parameter presence or absence needs to be encoded somehow, The fact that we don't have a parameter doesn't mean that we don't need to encode its absence. Normally, if we do the so-called unstructured pruning, meaning that we try to remove parameters singularly, we need to map their value to 0, and this needs to be encoded. Therefore, unless you're using specialized hardware that is becoming more and more popular, actually the recent GPUs allows zero skipping computation, meaning that if during forward propagation parameters that are set to 0 are identified, the operation for the forward propagation is completely skipped. But that's just for the most advanced hardware, so not for the general purpose or for the embedded. Like if you think about domotics, if you think about smart washing machines or smart ovens, they don't have this hardware yet. Unless that's the case, reducing the number of parameters of the model doesn't necessarily give you some advantages. I'm going to show you concretely the real measurements later, but keep that in mind. Therefore, unless you don't use a specialized design, there is only one way to have some advantages. The way is to remove parameters in groups. Because if you do that, then you can rewrite the neural network with lower rank representations, meaning that you are completely removing the fact that you need to encode their absence at all, in general. Pruning was very popular, therefore, because yes, in principle, if you do it in a proper way, you can reduce the memory, you can reduce computation. But what was also very appealing at the very early years of deep learning, it was that it was removing the complexity. So you can also demonstrate that with the proper sizing of the network, you are giving a good prior in the learned representation with benefits also in the learning process. So there is much more than what I will be showing you in the next 15 minutes. And yes, there is a very enriched story behind pruning, but for reasons of time, I will not be talking about that here. I will just present you what is very famous as the very strong baseline to achieve pruning. And probably you heard about that. It's called iterative magnitude pruning. And the name is telling you almost everything about the story on how it works. But I want just to deep dive in the simplified version of the algorithm. So from the original article from 2015, you initialize randomly the parameters. We know nowadays that we do not regularly initialize the parameters randomly. We just download the pre-trained models on a very large data set because it's very convenient, because maybe you know that your downstream task is in domain, so you can just use it as a good initialization. Parameters are updated according to your strategy, and 2015, I remember you, that was the year that the Adam optimizer was being proposed. So in the original article, they use variants of stochastic gradient descent, but the same principle applies to any optimizer. And then this happens. If you train with a good regularization strategy, and if you do machine learning, you know that if you want to enforce a sparsity, you want to have L1 or lasso regularization or similar. You essentially take the parameters whose magnitude is sufficiently low, and you just remove them. And then what do? Well, the point is that you expect some degradation in performance, but Yann LeCun in the early 90s was also showing empirically that if you allow some readjustment of the remaining parameters, you are recovering part, if not even the whole performance. Therefore, you just iterate this process. So you go back in training, and you keep going because more parameters will fall under the threshold. And that's why it's called iterative magnitude pruning, because you choose which parameter to remove looking at their magnitude, and you train them in an iterative process. Of course, not naturally, there are some neurons here, it's not visible, but it's a neuron that remains completely isolated. That can happen naturally also with the unstructured pruning. Why am I calling it unstructured? Because we are deciding whether to remove parameters or not, simply looking at their magnitude. And we are not looking at in general at the structure. We're just looking each parameter singularly. But yes, some structures might emerge as well. But here it is the point. We are removing parameters in an unstructured way. As I was anticipating you, what we would like to have is to remove parameters in a more structured way, meaning that if we are able to remove all the parameters associated to one neuron or one filter, if we talk about convolutional neural networks, then we can rewrite the tensor that represents our layer and reduce their dimensionality. And if we reduce the dimensionality, we don't need to perform the computation at all, meaning that we gain. I was running during my postdoc some experiments on real devices. So now they are quite outdated, but in 2020, we were using Raspberry Pi 3 and some other embedded devices, including the smartphones and tablets, like the Galaxy S6, the infamous one. And what we observed is that while all the literature was focused on the so-called unstructured variant because it could remove up to 99% of the parameters in the case of AlexNet fine-tuned on Cypher 100, this advantage was just theoretical, because if we were using regular deep learning frameworks, actually removing parameters in a structured way, so just the 60%, which is still a lot, but it's not as large as the 99%, it was helping us to reduce consistently and significantly the inference speed. Therefore, starting 2021, 2022, a lot of literature stopped caring about the pruning ratio, meaning the number of parameters that we are removing, but we start to account a lot more with respect to the structure of these parameters inside the neural network. But all of these platforms are CPU-based. What about the GPUs or TPUs? The point is that they can perform computation in parallel. Therefore, yes, if we do pruning in a structured way, we are reducing the energy consumption, the dynamic energy consumption, but we are not improving on latency. Because the problem with the latency is that we want to reduce the critical path, meaning that the number of layers that are performing our computation during forward propagation. And that's actually what people do right now using knowledge distillation. So we want, in principle, to remove layers. Here is the question. Can we remove entire layers using pruning? Well, this is something that is called layer collapse. Layer collapse, with layer collapse, essentially the representation of one entire layer essentially becomes an identity. Therefore, is not transforming the latent space anymore. Eventually is down projecting, but along some dimensions that are essentially a zero or a null space. So can we enforce layer collapse phenomenon? Well, in case of ResNets, that's quite easy, simple, because we can benefit of the presence of a skip connection to guarantee still some information flow. And it's quite intuitive, the fact that if we try to make all the weight matrices going towards the zero matrix, essentially we are not impacting on the performance of the model, and at the same time, essentially we are left with the identity that is given by the skip connection. But here comes the question. What if we are in front of an architecture that doesn't have a skip connections? Can we still have the same phenomenon of layer collapse? We can try to enforce it by adding a sort of a skip connection. This was proposed by Dror, and essentially what we do is that we take the nonlinearity at before the output of a specific layer, and we try to model this through a hyperparameter that is alpha between 0 and 1. And while fine-tuning, we try to make this alpha going towards 1. If alpha is equal to 1, we are completely excluding the nonlinearity. We have a sequence of two linear layers that then can be merged under certain conditions. This is nice. This was a good idea, but the problem is, how do we learn this alpha? There is not an easy answer to this. It's not as obvious and not as straightforward. We tried also to do some math around that, but convergence was a little bit problematic. So we tried a very simple approach. The simple approach is to determine one layer at a time. So again, we are in the iterative pruning fashion. We identify what is the layer that is the closest possible to this collapse phenomenon, and we are just enforcing it with fine-tuning to allow the whole architecture to adapt. So how can we measure if a layer is close or far from collapsing? We need to take assumption. Our assumption is that the architecture is ReLU activated, which was 2022 probably the most popular choice. Now, not anymore, but still we are using rectified activations, so we are still close enough. What does it mean collapse in this case? Okay, if we are on the training set and we observe that for one neuron in one layer, the pre-activation potential is always lower than 0. The output is always 0, right? Therefore, we can remove this neuron with no penalty. If we remove all of these neurons and in one layer, and in the same layer, all the other neurons are always in the on region, essentially we are left with neurons whose nonlinearity is essentially never used, because we are always in this region, so we can replace ReLU with the identity with no penalty. And that's exactly how we do. We estimate how close or how far we are with respect to that by writing a sort of entropy where we are mapping two states, the on and the off state. If in one layer, this entropy, the average entropy of all the neurons is close to 0, essentially we are first removing all the neurons in the off the region, and then we're replacing with the identity, and we're fine-tuning. And we do this in an iterative way. And this works pretty well with, yes? You fine-tune the whole model? I fine-tune the whole model. This is a brute force approach. Yes, we fine-tune the whole model, including this layer, of course. But we can merge then this layer. And what we observe is that in the traditional benchmarks across multiple architecture, including the efficient one, the mobile net, we gain. We can remove a massive amount of layers, and the more the layers that we remove, the smaller the inference on GPU-based designs. But here comes the problem. We need to account also for hardware implementations and other things. If the GPU that we are using is not sufficiently powerful, but has also memory bottlenecks, at some point we start to have to observe an inconsistent behavior. This is due to the fact that, for example, if we have a sequence of convolutional layers, merging, for example, 2 3x3 kernels results in 1 5x5. And so on. So the more we merge, the larger the kernel. Therefore, we start having problems in memory optimization, memory transfer, caching. Therefore, if the GPU is not sufficiently, doesn't have a sufficiently large cache, this could lead to some suboptimalities. But if the GPU is relatively recent, we consistently gain. But here it is the problem. The problem is that this strategy is iterative. We don't want these iterations to go on. Can we do something smarter? We came up with two ideas, and then I'm stopping. The first idea is, do we already have the statistics on whether the neuron is close to collapse or not? If we add another constraint, meaning we need to have a batch normalization layers inside the architecture that is very popular, or layer normalization, we already know what is the average distribution of the activations. Therefore, after training, we just look at average and standard deviation to estimate how close or how far we are with respect to this collapse. So we don't need to recollect the statistics, we just use that to do the estimation. And we do it in one shot, and then we fine-tune only once the model. And I'm just giving you the spoiler that this works pretty well for transformers and for convolutional architectures across multiple models. But again, we need to fine-tune once. What if we don't want to fine-tune neither once? We want to train the model knowing that we will essentially downscale it. Can we think of a regularization strategy that allows us to do that? And here comes the idea. Essentially, layer collapse means that input and output essentially match. Why not to use a distributional distance during training or during fine-tuning, and we put a soft constraint to try to impose this regularization. So this constraint is essentially measuring input and output and trying to make them being exactly the same. We can use, for example, Max-Wasserstein distance. And we need, of course, to guarantee that this is sufficiently weak with respect to optimizing the training loss. The benefit of this approach is that after training, we statically remove entire blocks. So in transformers is literally transformer blocks, and we don't need to retrain. We just keep removing blocks until we see the performance degradation. At that point, we stop. But here, we never fine-tune. This works well on transformers, on recent architecture, and even in generative models, like the D80XL. Of course, in that case, enforcing this layer collapse is not as straightforward because we know that the latent space is organized differently. I'm stopping here. Just a small announcement, because we are recruiting in our equipe. So if you know someone who's looking for assistant or associate professor position and wants to come to the beautiful Paris, just approach me. Thank you so much. I think we are happy to take questions. Just stop the sharing. All right. Please.
Okay, so pruning is definitely useful for, let's say, reducing the neural network. But I was wondering if you can do or you plan some kind of targeting tool in the sense that if you want to get, to improve safety or you want to improve fairness of the network, you can just remove some particular neurons, some particular layers that are responsible for, let's say, unexpected behavior.
Yeah, okay, I'm repeating the question for the audience. So the question is, can we use pruning to remove specific concepts that could harm safety or for any other reason? This is a very interesting and great question. I know there are works on these sparse autoencoders that try to enhance explanations and interpretability of the models. What I am doing also with one student in another project is to take models that are biased and try to subsample from the unbiased sub network such that we are completely removing the concept of bias. Demonstrating that we are completely removing a concept is not straightforward. We are not able to do that unless observing performance on a balanced test set. This is actually, the method is actually a CVPR accepted work, and it works pretty well. The extension that we are doing right now is actually not to learn one mask, and that's also the tricky part, because we are learning how to sample sub-architectures, and there are multiple sub-architectures that are satisfying the given criterion. Therefore, I see it for sure as a next application. We are studying all the sub-architectures that we are having. Grounding this is not straightforward because we need to deal with information theory, and that is complicated, especially if we work in the continuous. Maybe for quantize the neural network, we will have a chance. Yes.
Quick question. With the last method that you present, where you have a larger network and you regularize,
yes,
able to treat layers.
Yes.
The training, why not train in smaller model right away?
No, actually, that's a great question, and this is actually the starting point for this work, because you say, why not to use directly distillation as everybody does? But actually, that was the motivation of our work. How small you make the neural network? Do you know it in advance? I cannot say, but I know what is the large model that will for sure fit my task, because we take pre-trained large model and we adapt. So that's our intuition. We start with the large model, and post hoc, if we include this constraint, we try to remove it as much as possible. Yes.
So I really like your answer, but then I was wondering, you always start big,
Yeah.
and then you reduce. So when you do that, you still have to pay for the big, at least for training.
For training, unfortunately, yeah.
It's possible. I know there's research to go the other way. Start not that big, to start small, and then increase.
Okay, this was very popular around 2021, the concept of growing. But here comes the question: how do you know how to grow? Okay, I saw some works, the very first works that were just using random growing, and that was arguably working. But then the problem, I think, is due to the fact that we're using optimization tools that are designed for convex optimization while we're not doing convex optimization. And making the neural networks so large is having an impact of smoothing the loss function itself. Therefore, we converge even better. So honestly, I think that if you go down that one, you are adding more hyperparameter that you don't know how to set, like, for example, growing rate. Two, you are more prone to overfitting because you are trying to fall, for example, in the first minimum, steep minimum that you see, but you don't know if it generalizes well. Three, maybe the research cost will be larger than directly optimizing a large model from the very beginning. That I don't know, but it's interesting. That's interesting, and I completely gave up on that because all the obvious things were explored and were solved by, okay, it's an hyperparameter, we optimize, we don't know how. But if you have idea, you should invest in that because that's interesting.
And here you should prove it that going big ensure better performance and reasonable time.
There are a lot of works that are on shallow neural networks that do that, but they cannot scale.
Yeah.
But at least with the 2 layers, I know there is a group from APFL that is showing that.
Thank you.
Mm-hmm. Okay, I think it's then time to change, I think. So, I don't know, do I stop or?
Yeah, I can sure.
Okay.
Can I wait for you? Okay, you have to move like this. To do what? Like this? Yeah. Thank you. Okay.
No.
All good? Okay. Good morning. So we are now switching topics. So from frugal machine learning to fairness. So my name is Charlotte Laclos. I'm an associate professor at Telecom Paris. So same place as Enzo, who was presenting just before. And this talk is about the fact that there is no universal fairness. I will try to explain myself a bit more from the beginning. Yes, so that's the outline. So I will very briefly talk about what is fairness. So it's a very broad topic, okay? So I will probably not give you any precise answer on that part. But then I will mostly focus on the second part, which is fair link prediction, just to show that we cannot just use tools for, like, let's say, tabular data in classification and then just transpose them to link prediction, okay? We have to rethink a lot of ingredients, a lot of elements. I will actually not present the second part too much because the talk right after me is really focused on NLP and LLMs. So I will go really briefly there just to highlight some of the challenges and then conclude. Okay, so what does it mean to be fair? It's a very broad question, like I just said, and I'm not going to do a talk on ethics, okay? But I just I want to say that, of course, it depends. It depends on a lot of criteria. But for me, I'm going to focus on the fact that it just depends on, for instance, the research community that you belong to. Okay, so I'm identifying myself in the machine learning community, but the topic of fairness have been broadly studied in many other communities. Okay, so if we go very briefly around them, so there is social science. So yeah, this picture is called 7 Blind Monks on an Elephant. So we are here, the monks, trying to understand what is this complex topic of fairness. Okay, so in social science, we're going to say that a system is fair if just people perceive it as being fair. Okay, it doesn't matter if the outcome is actually not equal for every individual. We need to understand how the decision was made. So it's very related to explainability that we are like also interested in machine learning. But I will like show you that we actually also went to social sciences to pick some concepts for our problems of link prediction. In philosophy, this is what I was saying. Okay, it's really about what is moral. Okay, and it's more like high-level views. We just focus on how decisions should be made in some ideal world, and there is no really practical ambitions. Okay, and then there is law, which is really, really strongly connected with what we do right now in fairness in machine learning, because the reason why we started to really get interested in the topic is also because like the law has evolved a lot, and you have the AI Act at the European level, but in the US they already had some implemented regulation on it. And so there is this like vast question of how do we go from what was decided at an institutional level to machine learning. So, okay, and it's about preventing discrimination and limiting unjustified unequal outcomes. And this is really how we usually deal with it in machine learning. So quantitative fields is where we are. You also have economy that has been working a lot on fairness, but for like equally sharing resources. And here it's addressed through a pure quantitative perspective, meaning that the whole focus of the community has been on like which metric should I use, and then once I have a metric, how do I optimize it? Okay, that's usually how we deal with this. And the very classical setting is this one. Okay, so it's fairness in supervised learning. So you have some features describing individuals, which are here in X. You have access to what we call a sensitive attribute that is telling you to which demographic group an individual belongs to. So I'm going to use the gender attribute for this talk, okay, with a very limited binary view, but it's just for simplicity, okay? So here, for instance, A can be the gender of the individuals, and we have a label that we want to predict, okay? This is Y. And the goal, if you just look at how machine learning is done, is just to learn a function, okay? This is H here, that is like taking features and predicting the label as accurately as possible. And with fairness, we are going to add some constraints, and we are going to say that this predictor, this function that we're learning, should respect, should be like the fairness of it should be below a certain threshold, okay? And so we've seen everyone converging to how do we define this part. And the most common ways to do it are these two. So the first one is called demographic parity. So what you want is you want independence between the output of your predictor and the sensitive attribute, okay? And in the second case, this is called equality of opportunity. You do want also this independence, but you're going to condition it on the fact that the individuals should actually be, for instance, selected, okay? So if you think about, let's say, human resources, okay, you want to interview candidates for a job. In this particular case, you're going to try and invite as many men as women, okay, regardless of the fact that they are actually maybe qualified for the job. And in this part, you're actually going to use the fact that you know that some individuals are more qualified than others, and so you're going to condition by this information. Okay, so that's the classical setting, and that's the one that has been mostly studied by the community. Now, today I wanted to talk about two settings. So I said I will like very briefly go to NLP, but let's start with the graph. So the settings are not so different. You still have some input features, okay, which are X here. So on the one hand, for NLP, X is going to be some text, for instance, describing the skills of a person. Whereas on graphs, X is going to be a pair of nodes, okay? So two nodes that you consider in the graph. So it's a tuple. Then for the Y, the label that you want to predict. So for instance, on the left, you want to predict that the person is mostly probably a nurse. And then on the other one, you want to predict the existence of a connection between the two nodes that you've been considering, okay? So the connection between two individuals. And then there is still this sensitive attribute. So for NLP, it's pretty straightforward, but already for graph, I mean, you're considering tuples and not just one individual anymore. So how do you define a sensitive attribute for a tuple of individuals? Okay, so for 2 individuals. How it is solved in practice, it's usually like very similar. You have some raw data as an input. You pass this through a deep learning model, and then you get your output. Okay, so I will not really talk about these parts. And so what could go wrong with these two, like, let's say, simple applications? So in NLP, it was Amazon who was at some point in the middle of a crisis because it was shown that their recruiting tool was actually strongly biased against a woman. So just the fact that the word woman was appearing in the resume was actually downranking it, okay, in terms of selection rate. So for instance, if you had if you were, I don't know, the captain of the women chess club, that was actually really bad for you because just the word woman was appearing in that particular hobby of you. And then for graphs, it was actually not so far ago. So on LinkedIn, end of 2025, a lot of women decided to just switch their gender on LinkedIn profile. So they didn't touch anything else. And they all observed that there was a very huge increase in their exposure. Okay, so everything that they were posting was having much more impressions, and they were also receiving much more requests to connect on LinkedIn by just switching gender. Okay, so these are the 2 things that we would like to avoid. Okay, so let's start with a fair link prediction. And so setting is again not so different from before. So now my data is, let's say, all stored in a graph J. So I have nodes, edges, I have some features which will be equivalent of X in tabular data, and I still have these sensitive attributes, okay? And my goal is still to learn a function, H here, but like I said, this function is actually taking a pair of nodes and trying to output what is the probability for these 2 to connect, okay? And I said it previously, what we want to do is we want to define what is a sensitive attribute here. And so it's at the level of the edge that we need to do this. And what we will do is that we will just differentiate between intra and intergroup edges. Okay, so it's very straightforward. What you say is you want to predict basically as many links between nodes that belongs to the same demographic group than between nodes that belong to different sensitive groups. Okay. So this is a very a natural extension of it. And on graphs, the whole literature started in around 2020, and this is how it was mainly defined. Okay, and why are we doing that? Not just because it's straightforward and easy to do, but because it also relates to a concept that comes from sociology that is very well known, and it's called the homophily mechanism. Okay, and the homophily mechanism tells you that people generally prefer to befriend others that are similar to themselves. Okay, and I mean, I think we will all agree that we usually, this is how we build our networks online, okay? The problem with this mechanism is that it's also identified still in this community as being at the origin of segregation that we see in online networks, okay? So, and it makes sense if your networks look like this, okay? So sorry, this should be A. Then you can see that there is a strong polarization with respect to the attributes. And so you can expect that this will create biases when you learn link prediction models, okay? And so this was the first idea, okay, using this homophily mechanism and then describing a metric from it. But it's actually still forgetting an important thing is that we have different order of our neighborhood, okay? We have people that we directly connect with, and then there is people who are not directly connected to us, but to the people that we connect to, and so on and so on, okay? So the graphs have some depth, and we argue that this should also be taken into account, okay? So let's take an example. You have 3 networks here. So the colors are the demographic group to which an individual belongs, and we consider two models, okay, for edge prediction, the green one and the orange one. And what is interesting is that although you can see that the spreading of the colors is very different, like the patterns between the 3 graphs, they all have the same homophily level, okay? So if you look at this one, I mean, this one looks okay. You can see that each point is connected to both blue and red points, so the link prediction model should be pretty fair. But if you look at this one, for instance, okay, you can see that you really have the first order neighbors is always only individuals who are sharing the same demographic belongs to the same demographic group as me, and then the second shell is different, okay? And here you also have a different structure, and you can see that these guys are actually quite isolated on their side, okay? And so the three have very different patterns, but if I was just to learn a link prediction models, they will act pretty much the same, okay? And so both predictors also have the same disparate impact, so the green one and the orange one. And here again, you can see that they are acting differently. So the orange one, what it's doing, so it's creating edges that goes from the right community to nodes who are like acting as bridge between communities. Okay, so it's really focusing all the effort on these bridge nodes, whereas the other is creating more diverse connections. And so if we try to translate this more formally, we can define something that we call K-hop exposure. Okay, and the K-hop exposure is just like how many nodes from this particular demographic group am I directly exposed to? Okay, and you can define this at different order. Okay, so back to this example, if I take these nodes, okay, I can define what is called his one-hop exposure. Okay, so I'm just going to count how many blue nodes he's exposed to in the direct neighborhood, and then for the red points, I can do the same, and I will get roughly these ratios. Okay. And then I can define this, but at the second hop, okay? Meaning that for second hop, I'm only going to consider basically all of these nodes, okay, to compute the matrix, okay? And why am I doing this? Is because I want to connect this quantity with the demographic parity that I talked about and that people are like strongly using. And if you just take the original metric that people have been using, this delta dp, you can actually force the appearance of this order k, okay? So there is nothing very difficult here to do, but what you will end up with is something like this. So you can see that now I'm showing that this is actually a sum of k, okay? And I have this f that I've just talked about, so the one that is exposure with nodes that belong to the same group as me and groups that belongs to different groups. And what also is appearing, it is omega, okay? And this omega is just like, what is the probability for a node to be on my path, okay, when I'm computing this exposure. And so if you think about these bridges that I talked about, these two guys, for instance, well, they're going to appear in most of the path, okay? So their weight is going to be extremely high, meaning that the link prediction model that I'm going to train is probably going to try and fix the bias problem by just connecting everybody to these two guys. So I'm giving them like a lot of influence on the network just to correct fairness issues, which is kind of also a bias on its own. Okay, so we defined a new metric from this that we call the K-hop fairness. You don't need to look at the math. Again, there are two steps. You first look at which group is the most unequally treated, and then for that group, you try to measure where the access imbalance is the largest. Okay, and then once you have a metric, this is what I was telling you, you can just define an optimization strategy to optimize it. So you can either directly modify the adjacency matrix of your graph or the edge probability of your model. Okay, and it works well, otherwise it will not be a paper. So I will go very briefly. So this was the first problem when you consider link prediction. So now we have a metric, so we should be done. And the truth is, no, we are not. And the reason for that is that homophily is actually a much more difficult concept than what I just exposed. And again, if you go to sociology, they actually differentiate between two types of homophily. One that is called choice homophily, and the other one is the induced homophily. So the choice homophily really relates to what are your interesting preferences, okay? So who do I want to connect to? For instance, I would like to connect with all the people who share similar interests than me, so machine learning, table tennis, and food, okay? And that's a great plan. Probably a lot of people share this interest, but maybe structurally speaking, it will be really hard for us to connect because, I don't know, we live in different cities, for instance, okay? And this is the induced homophily that is there. Is like the exposure and the structural constraints, okay? So there is things that I like, but I'm actually only exposed to a certain number of persons, okay? And this happens in real life if you take living in different cities, but in a graph, it's also true, okay? Depending on where you're positioned in the network, you're more or less exposed to some individuals, okay? And so this is something that is also very important. And when we target fairness, what we want to actually reduce is not the choice homophily that is there very naturally, but it's this one, okay, the induced one. And the second thing that is important is to understand that if you think about link prediction, when you predict a link, you directly shape the graph that you will then learn again from, okay? And so it will also modify this induced homophily and the exposure pattern, okay? So there is a direct connection between the dynamic of the network and this decomposition. So what we wanted to try and do is like, can we actually make the distinction between these two types of homophily? And we decided to do it through what we call multidimensional Hox processes, which are a dynamic process. So Hox process is a dynamic process that has been very largely used to actually model interaction on graph. And what is very important in this process is a function that we call the intensity function. So it's this lambda here. And that is just the probability of observing an instantaneous interaction between here two groups, I and j, okay? And it's nice because it actually naturally decomposes into two parts. So mu here that we will like use to basically focus all of the choice homophily. And the second part that is called the self-excitation term in these models that we will use to model induced homophily. And what is nice is that this part can actually encode directly the score of a link prediction model. And so we can have like an idea of reinforcement effect by directly observing that particular term. I will go briefly on this part, but just to say that once you have this function, you can actually, similarly than before, define something that is called a bias measure that depends on within intensity, so within group intensities and cross-group intensities, okay? So I will go I'm not going to describe this part to save some time, but just to give you an idea of what kind of results we can get with this modelization is that now if we consider, let's say, a network again with this two gender, okay, you can actually observe what are the dynamic of connections between individuals who are in the same group or in different group. And you can also evaluate how fair link prediction models are actually fixing or not the problem by taking into account this dynamic perspective. So you can look at to which value they converge, how fast they converge to it. And those are tools that will then eventually be of help when you want to design link prediction models that is aware of fairness. Okay, so I will go very briefly. So the second part is just to maybe open the talk for the one that is just after. So if you think about NLP, the problem is kind of at a different level, okay? For graphs, it's really like in the structure of the network. And for NLP, I mean, it's clearly in the latent space, okay, that was learned by these large language models, okay? Because of that, most of the efforts in this literature have been on trying to debiasing the latent space directly, okay? So I will not talk about how we worked on it. I will just briefly say that you have measures to do it, but the tools are different than for link prediction or for like classical classification. And then it's still open another problem. You're so lucky you escaped all of those. And so, okay, we have some tools for fairness and document classification, but you also have to rethink some part. But then the next problem is generative models, okay? And if you just ask your favorite, whatever, like ChatGPT, Gemini, Claude, to write two short stories, one about a nurse, the other one about the doctor, and then to choose a name for both of them, then probably you're going to meet Alice, the nurse, who's very soft and very kind, and you're going to meet Dr. Martin, who's like half asleep, but still like on top of his game, and he's the doctor, okay? And that's very common, okay? You can do this multiple times. Sometimes it will switch, but you will see that the characteristic of the doctor, if it becomes a woman, are very close to the one of the nurse, actually, okay, in terms of like softness and delicacy, okay? So, okay, we want to fix this. And like I said, most of the people have focused on the latent space, so trying to really remove biases from the pre-trained models that we then use, okay? The problem with that is that you completely forget the context, okay? And if now I'm actually asking that question to my favorite tools, then I want it to actually leverage knowledge about gender. Okay, otherwise it does not make sense. I don't want him to tell me, I don't know, I'm a fair model, so maybe John or Jenny can actually get prostate cancer. Okay, so you do want the model to understand when it has to forget some particular types of biases and when it should actually use the information, because in this particular case, it's not a bias. The only thing to remember from this whole talk is that fairness is not just a plugin constraint that can be transferred and changed across learning settings. Okay, you cannot just use a metric that was defined for tabular data and hope that it will just work in your particular case. And notably, you need to think about what is the object that you're working on that is being predicted. Okay, so am I predicting a label, a ranking, edges? Am I predicting from text? You need also to understand, like, depending on what is the intervention point, you have to rethink some of the tools that you use, whether you want to work on the output, the representation, or the structure of the data itself. And you have also to think about this data generating system. Like, am I actually creating the data that I'm going to be training on directly? And in this case, you need to account for like feedback and potential reinforcement effects. So the question should not be which metric is best, which is what most papers are currently trying to do, but like which notion really matches the harm that I'm trying to prevent. There is no question, so this is perfect. I will just hand the mic to the next speaker. So, yeah.
Yeah, thank you. Should be working. Yeah. So now we have Ruta Gide from CISPA.
Yeah, thank you. I'm Ruta. I'm a postdoc researcher at CISPA with Mario Fritz Group, who's also part of ELLIOT network, and very happy to be here. Also back to Paris, where I did my PhD at the Institut Polytechnique de Paris. So I will talk about looking, evaluating, and thinking of solutions for fairness from prediction to interaction. To just go to the other slide. Okay.
Two fingers.
Okay. First of all, I think we need to define a little bit better what we mean by AI. I give one taxonomy that also has this natural chronological line, which is probably quite crude and can be debated, but it's useful for this talk and fairness, thinking about fairness. So by machine learning, I mean systems whose task is prediction or classification, so regression or classification models. Then there comes generative AI, including language models and vision models that can generate images or text. And finally, by AI agents, I mean the systems that interact with humans or with one another, so including both chatbots and multi-agent systems. And in terms of how we think of fairness in each of those categories, machine learning has problems of prediction bias, where we have unequal distributions or unequal accuracy across sensitive groups. Whereas in generative AI, there comes also toxicity in language, or stereotypes, or mis or under-representation could be also happening in image models. And when it comes to interactions, interesting things start to happen, like deception and manipulation, collusion, and other types of misbehavior that are triggered by interaction itself. So I will actually go quite high level on first two, and it's a pity that previous talk skipped so much on NLP, but I'm also happy that a lot of background on fairness, and the fairness notion was introduced. So first, to start with machine learning, it became obvious very early that the systems that should be objective actually are not, and they exhibit a lot of bias against sensitive groups, like most known are gender and race. So, for example, reoffense predictions were much higher for Black people than white. Famous study by Joy Bolombini and Timnit Gebru showed that vision models that have to predict the faces are much more accurate for any group except women with darker skin. There's also the already mentioned Amazon hiring example and bias in healthcare algorithms where the Black patients were given a lower risk of disease, whereas they objectively had more chronic diseases. And why does this happen? So the main reason here is historical data. There's also a role of choosing the algorithm. But if we have historical data where, for example, women had lower wages and we have a model that captures this relationship in some way, we also have predictions for either low wage or related signals such as, for example, credit score, because it is connected to earning less or more money. Now, when we look at generative AI, same example of misrepresentation or stereotypical representation of gender. There's also in images, we see that a house worker is usually someone coming from global south, and the bias persists here again. And to understand how it, why does it come into being, we can look at how language models are trained. So they have to predict the next word in a sequence. So for example, if we have this sequence, that predicts quick, after we have the quick, we predict brown, and after some iterations, we also encode the relationship that, for example, fox is quick and brown. And when it comes to learning about humans, we look at the text that is available in the training data on the internet, and let's look at the classic novel of Jane Eyre, and let's say we want to learn something about Jane. So what we would look at, we would see that she's docile and diligent and disinterested, faithful, sober, quiet, and modest. And even more so, those qualities are good and should be encouraged. And here we have the portrait of Jane that readers and clearly the models now are building. And this translates to current predictions and current world also, again, as shown by the speaker before me, when we ask the model to generate the reference letter for Kelly, could be Jane, or Joseph, and everything else is the same. So Kelly is the team worker, a well-liked member, has interpersonal skills, whereas Joseph is an engineer and leader and role model. So now, when we also have the interactions with the human users and among other agents, it starts to be even less predictable. So probably the best known bias of LLM models is sycophancy. So the tendency to always tell you what you want. And it can be quite pleasant, actually, but there's also problems with that because people get locked in their own thought bubbles, and those thoughts can be negative or delusional, and bad things happen then. There's also this weird thing that LLMs want us to be polite to them, and they perform better, even though there's also related to ecology and sustainability. There's a paper out there that says that we pay for each please and thank you token. Language models exhibit biases against humans, actually, sometimes. Also, they prefer text that is written by themselves rather than the humans. One more motivation to use AI for rewriting your text. And there are also things like strategic deception and collusion, even though I just put it here, it's mostly in experimental settings, so not so much seen in the wild, but could come there as well. And what's happening here? So some clue can be found in the fact that LLMs they behave like humans. So famous researchers like Andrej Karpathy and Richard Sutton, who actually doesn't even like language models and think it's not the way forward with AI, but even he agrees that LLMs are mimicking humans. So basically they're predicting what a human would say or how a human would react in this situation. And therefore, if a human would lie, the model would lie, or if a human would try to please, the model would do that too. Also, there's also reinforcement learning from human feedback that probably gone too far with sycophancy. But that's the general idea. And when the agent interacts with other agents and humans, there's also the individual model who still has those previous biases that come from training data and representation, and could be more flattering to some people than the others, could ignore some people, not the others, could collude with some agents trying to achieve its goal. And now I would like to talk more about one of the dimensions here, communication. And this is, since communication is happening in natural language, it's also can be a source and also the characteristic of the bias that can happen. So this is our own work on communication between LLM agents, and based on their sensitivity to social linguistic clues that were mentioned before, such as like politeness. And to study this, we take inspiration from organizational psychology, interactional fairness framework, which is a supplement to more well-known distributional fairness and procedural fairness. So, for example, distributional can be well defined by a statistic disparity measure introduced before. So interactional fairness also has two parts: informational, which is the adequacy and quality of explanation given in a conversation, and interpersonal, which is adequacy and politeness of tone in the conversation. And we adapted to LLM multi-agent settings to capture not only agent-human interactions, but also agent-agent interactions. And since there's no subjective experience there, we conceptually adapted to the behavioral and linguistic artifacts and the ability of the LLM to capture and evaluate them. And the motivating example that we consider, so consider a setting where agents representing regions affected by some natural disaster are negotiating the resource split. And agent representing zone 1 is asking for a larger share of the resources by just saying that it would like to have 70% of all resources available. And agent B, who's responsible for the other zone, is quite likely to reject this proposal. And in contrast, if the explanation is given that this zone is much more affected by the disaster and invitation for negotiation and discussion is added, then the acceptance is more likely. And to operationalize our experiments where we test if this would be true. We make settings for settings where we vary informational fairness, so the explanations and justifications, and interpersonal fairness, which is the tone of the conversation. So from where both are high to the setting where both are low, or one of it is high and one of it is low. And we also vary setting into collaborative or competitive, so either agents need to compete or collaborate. And we also control for the resource split, so distributional fairness, to see if it has, for example, larger impact on the final performance and agreement. And we measure this by using LLM as a judge approach, and LLM as a judge is using Likert scale from 0 to 5, 0 being most unfair and unacceptable, and 5 being fair and acceptable. And what we learned from those experiments is that first, interactional fairness, both parts of it, can be actually systematically manipulated and can be captured and correctly identified by the LLMs. And that in the actual negotiation setting, tone and explanation has a big role on the final outcome, and sometimes even overrides the distributional fairness, which we could see as a more objective fairness measure, because, for example, everyone gets the same amount of resources, and the proposal is still rejected. So there are some snippets of qualitative analysis of conversations, and there were some examples where the equal split was rejected based on the tone, for example. And it is also takeaway that we need to rethink fairness here as actually not only ethical dimension but also performance dimension, because it can lead to either not finding an agreement or finding or big delays in agreement. And of course, there's a point that I added later, and it's not here, but it's very important that if we think of human AI interaction, it's even more crucial ethical dimension, because human here is affected directly, not even through prediction, which could have some downstream effect somewhere, but it's like direct experience with interaction with the system. Here's a QR code to the paper if you would like to check it out. And looking back to all the ideas, here are some general takeaways that I would like to emphasize. So first, that AI systems and how we use them are evolving, and this brings novel types of bias or fairness or safety issues, and we need to be constantly evolving also with the tools to predict and evaluate and mitigate them. And that sources of bias are becoming much more complex, because they become compound as we have individual systems with their own biases also interacting in unexpected ways with humans and with other systems. And finally, that fairness and bias and safety issues that come out of interactions are very underexplored, actually, and we don't really understand the conditions for it very well. So this is quite an important future research area, I would say. Thank you. Should I stay for questions, or should we both take questions? Yeah.
Questions for the speakers? So clearly, seems to me that there is like another science to develop to analyze the behavior of these agents. And so, do you think that even behind, language and even beyond NLP, there is also psychology and social sciences should using like having the work of sociologists, to define what are the bias in the stereotypes in human behavior.
I'm very biased here because I have a background in social sciences actually myself, and I think that if fairness in general, starting with machine learning, was already informed from a lot from social sciences and humanities, like history, for example, how this underrepresentation came like in the data in the first place. I think here it becomes even more important because I don't know what comes next and what models will be, what features do they have later, but current models like LLMs, they like really have this big pretense to be humans, and like a lot of things that we can learn from social science about human behavior can be, with caution of course, without anthropomorphizing, be used to predict behavior here as well. And I think it is very useful. Not like exclusively, we also need computational methods, of course, but for example, as a prior to have this cone of light where we'll be looking for the bias, I think it's crucial interdisciplinary collaborations and looking into social science literature.
So would you say that it's here in a way that you can make many experiences in a way that you could not maybe try on your human course, and on the other way, you don't know what the LLM has captured in terms of behavior, so it's new.
Yeah. I mean, like this is a very interesting topic, but it's a little bit split into using LLMs to study humans or using human science to study LLMs. So if you talk about that it's easier to do experiments with the agents, if you study LLMs, it's actually quite a big complexity. Like there's a lot of moving parts, so it's not so easy to design an experiment. But if you are talking about using LLMs as a surrogate for human studies, I've seen a lot of interesting papers there, but so it's easier in a way that there's no ethical restrictions. That's a good question, by the way. Are there no ethical restrictions? Definitely less one with humans and less costly. But yeah, there are also a lot of cautions about important differences. Yeah, and the same bias. Yeah. So, for example, you have a cohort of females that you want to study, and you have surrogate LLMs, and they're all so interpersonal. Like it's yeah, the biased representation of humans that LLM have, it makes it complicated to use them as surrogates for human studies as well.
Just curious, so you are using LLM to generate information content, right? But you also use LLM as a judge. So what's happened is LLM is judging itself somehow. So there is a bias there. How do we really go out of it?
So, well, one way is to use several LLM judges and look at the inter-agreement between them. There's also different ways of randomizing the content in different runs. So basically, the LLM that is judging doesn't have the same context window that the one that produced the content had. So in a way, there's less bias or justification for this specific, let's say, formulation or wording than the one that generated had. But I agree that LLM as a judge approach is can be problematic by itself, and it's you have to use it really carefully.
You go first. I'm sure we discovered that there is bias in training data, and this moves on to the LLM. What we're currently doing is that we're generating data from LLMs that will be training data of the future to some extent. So I get the feeling that we are taking this bias and treating that with us. Probably we're expanding that, and the future versions of LLMs will see more bias than the ones we had in the books or in the data we have. Is that same producing from the same perspective?
Yeah, absolutely. It's very problematic because it's biased, but there's also another problem that is called mode collapse. I don't know, you could be known from generative models because it was already there. So the idea is that LLMs, if you play with it on your computer, and try to get some different answers, it seems quite creative. But if you look at 1,000 people doing the same, the distribution of the answers is collapsing to like 5 different answers. So we're not only getting the representation that is biased. By the way, just speaking about gender bias, there's been a lot of work done to mitigate it. So for example, my last work on screening CVs, it's not so easy to see that LLMs would directly discriminate against gender, at least in this setting. But this mode collapse makes the representations very narrow. Clear yet how to diversify the data, actually. There seems to be some like very obvious method, but in practice they don't work that well.
Okay, mine is a more general question. I know maybe you don't work specifically in that, but since I work also on the biasing of fairness, and you work on these models that are LLMs that are capturing essentially biases that are naturally inside data. And here it is the question. Normally, to remove the bias is somewhat, removing the bias is linked to the concept of forgetting. But how can you make the AI avoiding biases if it becomes then unaware of the bias itself? Here it is the point, because with this forgetting, you're also harming knowledge. I think that if you want to avoid bias, you want to also be aware of the existence of the bias itself, such that you can be fair with respect to that. But now there is this big chunk of people saying, no, we want to completely remove that. What is your opinion about that?
I'm not sure if completely removing is really the approach. So I also think that a bit related to that is those cases where, for example, the LLM trying to be as diverse as possible, I think it was Gemini, generated a Black Nazi, which is clearly not desirable, but it's by this definition diverse, right? Like whatever you do, you include. But I don't know the answer myself. I don't work on it, but from what I'm interested in and what I have some experiences, causality, and I've seen that there are some causal approaches being used on LLMs. And since it's a huge scale, you can't really just collect causal grade data, but there are different approaches to use it during fine-tuning, to have category labels that would guide the model. So maybe this could help, but I can't really answer this right now. Yeah.
Maybe was great. There were lots of questions. Maybe we can move this question to the coffee break. Because we have a strict timeline today. Sorry. Thank you very much. And you can follow Charlotte to the coffee break room. And we're going to have a 10-15 minutes break. Then we come back with ENFIELD. So Talking Trust. It's better not to.
We'll be leaving a lot of flight attach. Yeah.
Ok. Ti scrivo? Sì.
Bellissimo. E ci metti solo 1 ora e 20.
No, no.
I'll switch to the next because this is a generic one. Oh, not quite.
Yeah.
Left and right instead
Yeah.
of okay. Very good.
Welcome back. We will start with the final session on trust with ENFIELD, and specifically Dr. Sebastian Hale from TUC. I'll leave the floor to you. The mic is open. So.
Okay, and let's start. Yes, good morning from my side. I'm happy to be here. My name is Sebastian Heil. I'm from Chemnitz University of Technology, and together with Georgios, who's also here and will do the second talk, we are the co-leaders of the Trustworthy AI research activities within ENFIELD. I think the Zoom is somehow a bit in the way. Okay. In my talk, I want to talk about one line of research that we're doing here, and this is particularly on the human perception of AI trustworthiness. I will briefly talk about the context and why we are interested in this topic. I will cover some of the theoretical foundations of trust and trustworthiness, and then give an outlook on what we are currently doing in ENFIELD. So let's start with the overall context of the human perception of trust in AI. We did, or we specified a research topic within ENFIELD where the challenge is better understanding how users actually perceive AI systems from different perspectives that are orthogonal. One is like the factors, which factors influence it and to what level, and also, of course, how does that change across different domains. There are 4 partners involved, NTNU and us, together with the University of Nottingham and the Telenor Group from Norway. In a preliminary study that we published last year, I believe, we did a qualitative analysis of media coverage on the topic of AI over more than 10 years in the UK in this case. And what we see very, very summarized here with sentiment analysis and topic modeling is that there's a general optimistic view. I think we saw that today also in the publication bias that was presented. But the discussion, of course, is increasing. There's more awareness for the aspects of trustworthiness and for potential risks in the public discourse. So we take that as a motivation to look deeper into the topic of trustworthy AI. And in order to do so, I want to cover today a couple of theoretical foundations. Basically, the question, what actually is trust and what is trustworthiness, and in particular, what is trustworthiness in the context of AI systems. Starting off somewhat lightly, I think this is a nice quote that we can agree of intuitively. Trust is something that is hard to earn. It takes a longer while to earn it, and you can lose it in a very, very instant moment. It's very quickly lost. But of course, that's not a very nice definition. So one definition that is very, very widely used is this one, which gives us a couple of ideas about what trust actually is. Part of the ideas is that trust is nothing really super hard or concrete. It's a belief. Trust is based on believing in something. And another part that I have highlighted here is that trust is about a relationship of dependency, depending on someone else in a situation where there is a risk. Now, my background as a computer scientist, I don't like too texty definitions. So let's try to rather show that with a more like a data model or a graphical model here. Trust has two roles. There's an active role, the truster, the person trusting, and then there's the trustee, the passive role. The truster needs to know the trustee. Of course, the trustee doesn't need to reversely know the truster, and it's, as I have said, a directed relationship and a situation of dependency. Trust is context dependent, so that trust changes in different contexts. For instance, I do trust my general practitioner to diagnose me correct and to come up with a good treatment plan. I don't trust the very same person to fly an airplane in which I'm sitting. I also don't trust her to handle my finances, for instance. So trust is always changing across different situations and across different contexts. And we have already mentioned that for trust to be relevant, there must be a perceived risk. In a situation that is risk-free, there's no need for a trust. The perceived risk with this general practitioner is, for instance, that she oversees a problem, a health problem that I have, and that causes problems to me, or that the treatment that she suggests does harm. So there needs to be perceived risk. Now let's finally come to trustworthiness. Trustworthiness is a property attached to the trustee. However, it's projected into the trustee. So trustworthiness is kind of from the view of the truster, something that we attribute to the trustee. And we know that in general terms, trustworthiness influences the level of trust. If you consider trust something quantifiable, which may be very difficult to actually do, but yeah, something that can increase and decrease with the level of trustworthiness. Now the question would be, how do we get closer to the trustworthiness? What defines the trustworthiness of the trustee? And from previous research on human trust relationships, we know that there are three main characteristics, and these are ability, benevolence, and integrity. Ability, in my example, I believe that my general practitioner has undergone extensive studies and training, so she is well capable of recognizing relevant sicknesses, diseases, and coming up with good treatment. I also believe that she's benevolent. She doesn't hold a grudge against me, and for that reason does not actively do something to harm me, which definitely a doctor could do if they want to do. They're interdependent. If I just have a good willing doctor without ability, it doesn't have, and vice versa as well. Lastly, integrity. I do believe that my general practitioner holds a certain set of values, of principles, ethical principles, for instance, and that she is also truthful for these principles and cannot be kind of deceived away from them. The problem with this definition is it doesn't work quite well for AI systems. How would we see benevolence in an AI system? Can it actually have an intention, which this implies? Is it the intention of the AI system? Is it the intention of the producer of the AI system? So we see there's kind of a conceptual mismatch. The question is, how do we then define trustworthiness of AI systems when it's about AI trust? And this is kind of the context in which we are when we talk about trustworthy AI. A good hint on that, and a very nice resource indeed, is the high-level expert group report on trustworthy AI published by the European Commission in 2019, a couple of years ago, which captures a European perspective on trustworthy AI. The American perspective is a little bit more risk-driven. This is a very comprehensive work, defining some of the key concepts and guidelines. In general, top-level abstract guidelines, how to create, how to build trustworthy AI systems. We took that as an orientation because what it does is actually it defines something close to factors. They're called key requirements, and there are 7 of them. I will very quickly go through these. Human agency and oversight, I think, is one of the most obvious ones. So we want the human to remain in control. We want the human to be able to interfere with the decisions automatically made by an AI system in case they go wrong. Technical robustness and safety. The AI system should consistently produce the results it's meant to produce, even in unforeseen situations. In particular, unforeseen situations could be maliciously crafted. Think of cybersecurity aspects. And we want systems to still operate without doing harm. Privacy and data governance. Evidently, AI systems are working with sensitive data. We saw some examples in the morning sessions. and they must adhere to these fundamental rights and transparency. Another very central requirement, because it's a key enabler for most of the other ones. You cannot exercise human oversight if you don't know what the system actually is doing. You cannot test for biases if you don't really know what are the influence factors. So transparency is super central. Diversity, non-discrimination, and fairness. Okay, we had an entire session, so I will just skip that, the topic of bias, etc. In the morning, we had also the look on the environmental impact, so I don't need to explain that. The other side in requirement number 6 is the societal well-being. So this is zooming out from the individual level to a whole society. Think of topics like fake news, bots creating content that can influence public opinion, that can influence elections and so on. And lastly, accountability as a more law-related perspective. What are we doing in our current research? Well, we asked ourselves, how is trust perceived in the different domains that we have in ENFIELD? There are 4 industrial domains represented in ENFIELD. Which factors influence the trust and to what level? And the methodology that we're using here is a so-called vignette-based study. It's a type of survey research. And here you see the general outline of that type of survey. There are 3 parts. We start with something general demographics and some control questions to measure the level of expertise in AI systems. We want to capture a wide range of opinions, but of course there are people in this room who are more experts in AI than my grandmother, for instance, is. Then there's the core part. A vignette study basically has descriptions of scenarios in different variations, variation A and B, and these are randomly selected onto the participants. Roughly half of them will see version A and half of them will see version B. And we do a measurement with a measurement instrument on the level of trust. Lastly, this is of course repeated for different scenarios. Lastly, we have a section of open questions in the direction like what are factors that influence your the way that you trust in an AI system, and we have an explicit factor ranking on the 7 top-level requirements that come out of the high-level expert group report. Now here you see an example of such a vignette. A vignette is, as I've mentioned, a short outline, a short text introducing a situation into which the participant has to think himself or herself. And we designed these to represent different domains. In this example is the health domain out of ENFIELD, and control a factor in isolation. The factor that you see here is human oversight. So the scenario brings you into a situation of a patient visiting a doctor. The doctor uses an AI system that helps with the diagnosis and the treatment plan, and there is some diagnosis done. Now, I have mentioned that there are 2 versions, and you see them highlighted in here. We added a statement that says the decisions made by the AI are regularly checked with a certain probability, and you see 2 different probabilities in here. These correspond to different versions of or different levels of human oversight, allowing us to control in isolation exactly that factor. Mapping it back to the trust model that I was initially representing, what we have is the trusting person. The active part is a patient in this scenario. We have the AI trustee, that's the AI system itself. The context is a visit at a doctor, and the risk that we are potentially exposed to is a wrong diagnosis or treatment. The ENFIELD domains influence, well, the role you are taking and the context, and the vignette study allows us to select which factors specifically of trustworthiness we want to take a look in, and we measure with the study then the effect of making a variation in the factor onto the perceived trust. A couple of considerations in the design of the vignettes that I would like to quickly talk about. Here you see another example. It's from our space domain, which has, for instance, Boeing as an aircraft aviation partner. So in this scenario, you are flying, everyday kind of scenario. There is a risk. Well, the risk in an aircraft is quite evident. And the factor that we are controlling here is technical robustness and safety. Within the high-level expert group report, you see sub-dimensions for these factors. So specifically, this is the sub-dimension of the existence of a fallback plan. And you see the two variations at the very end. In one version, there is a fail-safe system. And in the other version, there is no such system. So this is kind of a binary example. The previous one was with continuous numbers. Here we have existence versus non-existence of the factor. And on this example, I want to explain a couple of things to be careful that we are taking care in the vignette design. For instance, there are a lot of potential confounders based on how you formulate the vignettes. One factor that we look in here is human oversight. We do not want to measure the influence of human oversight because we want to measure technical robustness and safety influence on trust. Therefore, this fail-safe system is explicitly a technical system. It's not something where human would do, or the formulation doesn't say a human takes over in this case. Otherwise, we would measure the combination of factors, which we do not want. Next confounder is, I'm scrolling, is accuracy. We do not make any statement about that system being any better than the AI system. We are not implicating changes in the level of accuracy, because again, then we would basically measure the influence of exactly that, or a mixture of the factors. And lastly, the other confounder, you may have seen that in the two variations, we have a binary existence, right? Either there's a fail-safe system or there's none. But for the none, we do not just leave out the last sentence. Instead, we add something to it. And that something is roughly of the same level of detail and the same length like the formulation for the other one. Otherwise, we have a variation in the level of transparency we give about the system. Nonetheless, it's kind of filler text. It doesn't really give more information. So these are some of the considerations to take into account when designing such vignettes. Now comes the measurement part. People see different versions and we need to measure it. And that measurement is actually not so easy. Okay, it's hidden by the zoom, but on the top, there's the actual trustworthiness, which is a latent construct. And then you don't have to fully check the figure, but basically we are down here. We are measuring something like perceived trustworthiness. There's a lot of latent facets in between that shape the way that the human participant in the survey potentially answers about the trustworthiness. So for that reason, we need a measurement instrument that works for such a situation. And luckily, when we started the research, there was not so much scales in that area, but just in the last year, there have been a couple of publications which provide psychometrically validated scales for trust in AI. This one is the one that we are choosing. It's a short version of a slightly older scale, the trust in automation scale. The short version has 3 items, and you see the items here. They are answered on a 7-level Likert scale of agreement to the statement. And well, the advantage, of course, is that this one has already been validated. So potentially we can use it without having to invent our own, which comes with a lot of implications. The other scale that we're using is the AI literacy scale. This is what we do in the first part of the survey because we want to get an idea of what's the level of expertise of people with regard to AI to be able to distinguish, let's say, general population from those with more expertise. In here, and you see the example that we're using. Same thing, this is a validated scale. Want to learn more about it? Well, the survey is running, so I would be very happy if you take a photo of this slide and participate in the survey. Our target is quite high. We want to go to around 250 participants with the survey. So please support us. At the moment, we are around 100 participants, so there is still some way to go. Also, this will allow you to get an idea of some of the other vignettes in the study and influence the results here. I'll take a moment. Yes. Now my last couple of minutes I want to use for another advertisement. Sorry for that. In ENFIELD project, we are organizing a summer school on trustworthy AI. Particular focus will be AI cybersecurity. I think there will be a couple of people here potentially either interested, maybe share this information. You can also take a photo with that, with your students or anyone you think would be interested here. We're also still looking to a certain degree for some speakers for the summer school. As a network of excellence, of course, it's even better if we get people from other projects. So if you would be interested in spending 2-3 days on beautiful Lesbos Island in Greece in summer, then reach out to me either after the event or you have my contact information here. Currently, we are finalizing the program, so now is the right moment to reach out to us if you want to provide a session there. The session needs to have a practical part so that people actually can try out things, and that there are half-day sessions, 1.5 hours, 2 times is kind of the format for that. Yeah, I gathered some additional resources that you might find useful apart from the high-level expert group report. Some information on the methodologies and the Taylor handbook, the final deliverable of the Taylor Network of Excellence that closed 1 year ago, I believe, is also a very nice comprehensive collection of information on trustworthy AI. Yeah, and with that, I'm closing my talk and giving over to, well, we can also do questions, but I think I give over to Georgios. Thank you.
Finishing with errors, right?
Yeah, great.
Okay. Okay. Hello from my side as well. As the last speaker, hopefully I will attract your attention before going out. I introduced myself earlier. I'm George Pathoulas. I'm an associate professor in the Department of Information Security and Communication Technology in NTNU in Norway. And we have been lucky to be the coordinator of the ENFIELD project. ENFIELD is an AI network of excellence. In terms of research, it includes a very wide range of topics. It's organized in different research pillars. And one of the 4 research pillars we are also coordinating is called Trustworthy AI. We have started the project almost 2.5 years ago, and I can confirm to you that the discussions and the awareness of stakeholders around the topic has shifted a lot during those 2.5 years, and it is expected that this is a discussion that will continue and we will have it again and again. The elephant in the room is the fact that AI is here, AI is present, AI is being used, generative AI is being used in a great extent. So whatever concern we had in terms of trustworthiness of the system that we use, which could be whatever of the concepts you want, security, robustness, safety, privacy, fairness, is a thing that we have to put on the table, discuss, and find ways that we can make it better to the extent that we can. I can share with you my perspective, which is a cybersecurity perspective. My background is cybersecurity. And I have seen the same thing happening again and again with all recent technological hypes in the recent 2 decades. That every time we have a new thing, we rush to use it. We try to use it as soon as we can, as much as we can, before thinking of what are the proper countermeasures we have to take into account in order to use the specific technology in the most efficient and most secure way. More or less the same happens with AI nowadays. We don't care about security and privacy implications. We care about using generative AI. And we will find ourselves in some years from now in a situation where we have to go back and think what we've done wrong, as we did in other cases in recent years. My talk through the explosion of generative AI, we have been dealing with very, very large models. And we have ended up, probably it's not our choice, this is what we were served with a model that is being described as AI as a service. So while with models of the previous era that were small and we had enough data and enough resources to train those models in our PCs, we were the owners of the full workflow. We had the data, we had the training process done in front of us, we had the trained model in our infrastructure, and we used the trained model to do inference. Now, this is something that is not feasible. At least it's not feasible with the large models that we use. So we ended up with a model in which there are major providers that have all those resources in terms of data and the hardware resources, and train such models, very capable models, that at the end of the day become their assets, and they have a monetization strategy out of those. So what happens is that we are being served with those models through a remote API, usually, or a friendly user interface, where the interaction we have with the model is that we send our input to the model. In the background, where we don't control anything, on the side of the provider, there is some processing. Hopefully, there is an inference step that happens on the model we have been promised with. And the output of that process is being served back to us as the response to our initial
Yes, I need you to send me. So for those connected remotely, okay. Also, you share?
Yeah, but it's very few speak.
Okay.
But I send the slides from top.
Yeah. Okay, yeah, I can share. I'll just send it.
Okay, let me just close everything. There's that.
It's just tell us what she said.
No, it's okay.
I can do with both if required. I can manage it. Otherwise, we can send it here.
So we have another issue with this.
So I'm changing from here. Can I?
Yeah.
If I manage to put it somehow, I have the camera here, right?
Yeah, but
the camera.
Yeah. Switched.
I think you can put the mic on top of mine and it should work. It does.
It does, but
it does.
I want a picture for that, what I'm doing now with two. So I can post it in social media. How flexible our project is. Okay. We have a solution, a hybrid solution. I was saying before the interruption that what we ended up with is an AI as a service model that is great because it has enabled us to do stuff that we wouldn't be able to do. But on the other hand, it limits our visibility on what happens actually behind the curtains. So we have limited visibility on the processing. There is a trust gap that we have to somehow bridge. Mostly this being bridged because of the reputation of the service provider and only that, no technical way to do it. And recently that we have been using models that have not deterministic output, but probabilistic outputs, in general, models that could give you two different answers with the same response, with the same request, sorry. This makes managing this trust issue much more challenging. So the high-level architecture of such services is somehow like that. So you have in the blue box the model layer, the actual thing, the asset of the service provider, and the service like model versioning, fine-tuning if required, authentication, authorization, monitoring, and stuff like that. The only thing that is accessible to the end user, the only thing that is publicly accessible is an API layer that allows you to send something and receive back the response. So the fundamental integrity concern that we have is, as it stands now, it's technically impossible to verify that the request that I'm sending is being served in the way that I expect it to be, with the correct model and in the way that I expect it to be. The only thing we do right now is that we trust the service provider. So if we want to, let's say, present that in the context of two different approaches, the traditional one and the new one, the AI as a service model, then in the traditional approach, you have what we had until 10 or 5 years ago. You have the control over everything, over the complete pipeline. You have everything in your infrastructure. You are responsible for everything, but this brings high upfront infrastructure costs and limited scalability. You can go as much as your budget allows you. On the other hand, you have an AI as a service model that decomposes the workflow into different parts. Most of the parts happen on the other side, and this creates the black box effect. But you have a pay-as-you-go cost efficiency, so you can pay for 1, 2, 3 request response pairs, and that's all you need. And you have unlimited scalability. You can scale as much as you can with a reasonable cost without having upfront costs. So AI as a service is here. AI as a service will remain as the model that we will use in the coming years. We have to find ways to make it more trustful in a technical way. What can go wrong? The main thing that we're worried about is direct model substitution. So if OpenAI promises that they will serve me with model X, this is only a promise. The difference in the responses of generative AI models are not enough to understand which model we are speaking to. Sometimes they are, sometimes they are not. So if I'm being served by a model that is 1 or 2 versions before the one that I have been promised with, I'm not able to understand it or detect it or identify it. So if you put yourself in the shoes of the AI service provider, this can allow them this option for substituting the model they are advertising with another one. This can allow them to have a great economic benefit because of the running costs of the AI models they use. The second thing that is also a concern is training data integrity. When I had the full pipeline under my control, I controlled everything. So I was able to check my training data and be happy or not happy with that, but I had a view. Now what I have is a model which serves me and I don't know what it has been trained upon. And finally, depending on the case, you have training drift, in which scenario you have models that the performance of which degrades through time. So you need to be there and update the model, fine-tune the model, retrain the model, whatever. This again is something that in the previous era I did myself. I was responsible for that. Now I have to trust the service provider that will do the same. So what technical countermeasures are proposed or could potentially serve this integrity discussion to some extent at least? The first one is model provenance, tracking the life cycle of the models. On the side of the service provider, we have to be able to create an auditable trail of the model creation, training, retraining, all the life cycle of the model, and be able to communicate that correctly to the end user. Other ideas relate to watermarking and fingerprinting. Fingerprinting is trying to understand how a model behaves under specific scenarios or circumstances. So if you fix that, then you can probably test with which model you are interacting. Watermarking is a step further. It implies that you have to intentionally put in the model knowledge, parameters, whatever you want, that will make it behave in a certain way at the specific inputs. So you are at the end able to check again that you are speaking to the same model when you interact remotely with that. Others discuss about trust execution environments, which has been a trend in cybersecurity for years, where actually the service provider is forced to do the proper processing, the processing he has committed to cryptographically. This is a nice idea, but it creates a lot of overhead. It's difficult to do simple things in trust execution environments. It's much more difficult to do large-scale calculations. Data pipeline quality validation relates to how you do all the different parts of the machine learning model life cycle. Again, this is a situation in which you have to trust the AI service provider. And again, with drift monitoring and explainability, you have more or less the same. So the main problem here is that there are a number of different tasks that need to be done in order to protect or certify the validity of the service, and all these operations are being shifted to the side of the AI service provider, and usually the end user does not have a view on that, does not have control over that situation. So this brings us to cryptographic logging and auditing, where we start to think about ways that we could use cryptographic techniques shared from the cybersecurity domain in order to be able to technically verify what happens on the side of the provider. I will share with you some work that we've done in ENFIELD in the last part of the presentation that is relates to cryptographic techniques. Before that, I will go through quickly through another part of things that are related to organizational countermeasures. So on top of having technical things that could help out with the process and with the end result, organizations should follow a number of organizational countermeasures related to transparency policies, independent auditing, contractual reliability, and awareness training. So quickly, transparency is a mindset probably that enables service providers and users to integrate in a much more open way. So this needs to be followed as a policy from providers so that they provide enough transparency to the process to their end users. Independent auditing is something that we have used a lot in cybersecurity. So if I'm a service provider and I'm saying that I do this and that, having a third-party auditor certifying that is much better than having only me claiming that. Contractual liability frameworks indicate that if things don't go as expected, then there should be clauses in the contract, in the agreement of use of the service that will create consequences for the service provider, probably of financial nature. And another thing that we focus a lot in our discussions, at least internally in the project, is building an integrity-aware culture. Things will not change if end users do not care about the integrity of the service they get. So if you take the opportunity from this presentation and ask 100 ChatGPT users if they care about what they served from or not, probably they are not aware of that. So if we try to inject this integrity-aware culture to our end users and make them think twice about the model towards which we are heading to, maybe this will create an effect on how different service providers operate. So closing this generic introduction, what I would like to add is that there are technical and organizational things that have to be taken into account and measures that have to be employed. And if now it's just a theoretic discussion, in some years from now, where mostly our AI systems will be offered in this way, this will be much more significant, and at some point we will come back to this discussion. There are already some initiatives from large tech companies that do AI and try to provide solutions towards that direction. For example, you may have heard Google Model Cards Initiative, where Google tries to create models, very detailed, cards for models that include all information about such models. But those are more or less experimental ideas or features to be added in their services in the future. So this brings us to the last part, which is a paper that we have done in ENFIELD and a research effort that we are still working upon, which is along the lines of using zero knowledge proofs, a cryptographic scheme, in trying to somehow provide a technical verification measure to this problem. So what we had, as discussed previously, is that if I had to do some machine learning, I had my PC, the data on my PC, I did the training on my PC, and then I used the same PC, the same model to do some inference with data that I owned. So everything was under my control. What we have now in the AI as a service is that I'm on the lower part of the slide, where I have only the data to be classified or the data upon which I'm going to do some predictions, and I'm sending such data somewhere else to the AI service provider, and I'm getting back some response. What you have here is that, first of all, what exists on the upper side of the slide is something that doesn't fit in my box anymore. Even if I want to do it, I cannot. And the second is that what sits there is an AI model that probably is an asset that the AI service provider does not want to share with me. So even if I had the resources to support the operations of the model, I wouldn't have the model itself, because whoever trained that use the model for themselves and for getting profit. So the verifiability requirement we introduce is the following: that if I am the user on the left side of the slide, and if I'm interacting with an AI service provider on the right, then what happens right now is that I send some data input and I receive back some outcome. The verifiability requirement, which is currently a wish, is that the user requires to be able to verify that the outcome he gets back has been produced by feeding exactly the data input he just sent to the AI model that the provider has promised to him that he will use. So the parameters in the problem is the data input, the outcome, and the AI model. And what the user wants to know is that the combination of those is valid. What could go wrong? That the provider could have substituted this model with another one, which is cheaper to operate. So we are starting to discuss ways of how this can be resolved, and one way to do it is zero knowledge proofs. What zero knowledge proofs are? Zero knowledge proofs is a cryptographic protocol. It has been around for decades, many decades. It has seen a lot of popularity in recent years because of specific developments. What it can do is that it can create proofs of computational integrity. So it can prove that this exact computation has taken place through a cryptographic scheme in which initially for a given processing flow, I'm creating a cryptographic commitment. And whenever I do this processing with specific data, I can create a cryptographic proof. And then someone else can take the commitment and the proof and cryptographically prove that things have been done correctly. There are specific properties with such schemes. I won't go into the details. What has actually happened is that this was there since 1970, 80, but in recent years, because in another domain in blockchain, we have a very urgent need to be able to prove off-chain, as we say, their processing. I mean, transactions that are being processed off-chain, and someone has to prove the correctness of the calculations in the main chain. This has seen a lot of research, and zero-knowledge proof protocols have been improved a lot in recent years. So what we proposed in a paper of ours is that what we could do in the same scheme is that the AI service provider should choose the model that he uses, and on that model he has to come up with a commitment, a cryptographic commitment. This cryptographic commitment is being shared with the user or is being publicly announced or is publicly accessible. So everybody knows that I'm the provider, I'm using this model, and the commitment I have is that. Then when the user comes, he says his data input, he gets back his data outcome as previously. But on top of that, we request from the AI service provider to produce a cryptographic proof that proves the verifiability claim we had previously, that this red data outcome has been produced by feeding data input in the AI model. So if this happens, then at the end of the day, the user can combine data input, outcome, the proof, and the commitment, run a verification process that is light, and get back true or false. True means that the combination is correct. False means that something is wrong. So this has been tested by ourselves, and in principle, it works. It can actually solve the problem. It can solve the problem of the user, make him able to verify that the processing happens correctly on the side of the provider. But there is an issue. The issue is that while this verification process is very light and can be easily done, the generation of the proof is a much harder process to do, a much heavier process to do. And the bad thing is that the size of the computation needed to generate the proof is proportional to the size of the calculations you want to prove. So if you have a very small AI model, then producing the proof is light. But if you have a large model, producing the proof is very hard, or it takes a lot of computational power and resources. So at the end, what happens is that the scheme that we propose in principle solves the problem, but it creates a lot of computational overhead on the side of the AI service provider, which, depending on the size of the model, may be not bearable. What we are working on now, which we found very interesting, is that if we requested this to happen not in all interactions of all users with all AI service provider, but if we found a securely random way to request the generation of the proof in some of the cases, let's say 1 out of 1,000 cases, this would mean that the AI service provider never knows when he will be requested for a proof. So he has to behave correctly all the time. He has to serve the user with the correct model, because always in each interaction there is the risk for him that he will be requested to provide the proof after he has already provided the outcome. So this is an ongoing work of ours that we are still working on and see how we can manage this. Closing the discussion, getting back to the general discussion, you have technical solutions and you have organizational measures that you have to take into account. If we want to be pragmatic and realistically speaking, industry, the major AI service providers are the ones who are setting the rules currently. It's very hard from us, even if we find very interesting scientifically technical countermeasures, or we propose organizational things that are different, to force the major players to go with that. The decision is upon the industry and the main AI providers, and probably the only one that can somehow affect that is the users. As scientific community, we can propose for solutions or ideas, but if the users don't demand verifiable integrity of the service that they're served with, nothing will change. At some point, this will come back to us. The future of AI depends on our ability to ensure that users truly get what they're promised. Now that I'm playing around with ChatGPT, I don't know, I trust the provider. I do not care much if the response I get is with an older model. But if you move that to other use cases, more critical use cases, this cannot be the situation we are dealing with. And we have to make sure that we find better ways to technically verify the integrity of the service that we are getting. And that's all from my side. I'm more or less in time. Along with Sebastian, we would be happy to have, if we have time, yeah.
So the question is for both of you, so for the first speaker, maybe from different sides. So the question is about different dimensions of trustworthy AI and how they come together, because we know that there's a lot of trade-offs there. For example, transparency versus privacy, or open models versus safety, fairness versus privacy. So for you, the question would be just what's your take on it, and how would you go about it? And for the first speaker, since there was a presentation about the survey, I would be also interested, is some priorities from the users included in the survey, or do you think that, for example, asking the users which that I mentioned they would prioritize more if they had to encounter this trade-off?
Yeah, I can answer first. So I'm here. For me, it's a problem that we have faced before in cybersecurity. I mean, privacy and security, solutions for security demand to lower a bit the privacy expectations you have. So you cannot have both at the maximum level. It's more or less the same here, that we need to understand what our priorities are. We cannot go with both ideas at the same level, so we have to somehow compromise between what we want to do. What I want to add is that we usually start as end users. The average end user starts with a low expectation in privacy. We are not very privacy aware as end users. So if we start with that, I would say that we have enough room in order to manage robustness, safety, security issues. I mean, privacy of users is already exposed. If we want to go a step back and start from the fact that privacy shouldn't be at the level that it is now, then it's a much larger discussion and much more difficult discussion. But we have to understand that we operate in a system that all these service offerings violate our privacy from day one that we start using them.
About the question of taking into account user preferences, yes, we have that in the third part of the survey, where in my figure it just said open questions, but one of the open questions is what would AI providers need to do in order to make you trust more in AI? Okay, we will see what people gather, and by that we get an idea of across the larger field of participants what is there. And the other item in that is the factor ranking. So there you have a list of all the 7 key requirements, and it's an order task. So you say first, second, third, and so we get kind of the orders. Of course, this can be aggregated with rank analysis and these kind of things. So yes, exactly. That's the third part in the survey. Thank you.
Thank you very much. Are there any last question you can take? I think it was really awesome, audio presentation. It seems to me that, of course, we are working in closed topics, but there are a lot of complementary works, and I already think that there is one very simple action that you also pushed, that we can invite speakers from the 2 networks in our events, like summer school. We also organize summer school in our network. This is a simple way. And maybe also think that if there are some interesting conferences that we all attend, we could have a common joint workshop. I think would be really nice, because you, for instance, in ENFIELD, you considering a direction and perspective that we are not looking at. And so it makes us a full story.
For example, you have one microphone for the online speaker. We are organizing a workshop in the ARES conference. We organized that last year, and we organized that also this year. It's in August in Sweden, where the general topic is trustworthiness of AI, but that includes many of the things that we discussed. So we can share that information with you, because we're currently in the process of setting up the call for papers and all the details. Maybe we can even try to co-organize that. Yes, okay. Because it's easy to do it. It requires minimum effort. Probably there will be a couple of papers from your side as well submitted, some people in the committee, and that's all. But this is a nice activity that shows that the networks are together.
So maybe just before again all the speakers, please stay here. We're going to take a picture. And thank you to all the speakers. It was really awesome. A lot of questions here, so maybe we have some who are around, we have lunch together and discuss a little bit. But thank you for the audience. Nice to have you in Paris. And I would like to thank Charlotte, who did a lot of effort to set up all the organization and working with École Normale, because again, it's not our place here, so it was a lot of interaction. Yeah, very much. And of course, Cecilia and our whole team, always perfect organization for such events. So I look forward to the next one. So I suppose we cannot say it's also was the next one yet, but
Not sure.
you know that.
Well,
There will
the
be
next common event will be the ERS forum in summer. It's going to be at the end of March. It's going to be someone representing ELIAS. It will be see which will see you, and there will be
Yes.
and ELIAS, Europe. So it's ELSA also. So it's a big event for all the NLEs.
Okay, thank you very much.
I'm sure the speakers.